Good morning everyone, my name is Shoffan Saifullah and today I'll be presenting our research on forecasting method with the title Seasonal Mid-Stock Demand Used Comparison of Performance Smoothing Average Forecasting. This work is a collaborative effort with my colleagues from different institutions, me from IJEECS University of Krakow, Poland, Tundo from STIKOM CKI, Indonesia, Dharmawan from Universitas Jember, Indonesia, Junaidi and Elmi Devia from Universitas Krishna Dwipaya, Indonesia. We aim to address the pricing need for accurate beef stock forecasting in Indonesia. This research was accepted for publication in the Indonesian Journal of Electrical Engineering and Computer Science in 2024. Here's a brief overview of today's presentation. We'll start with an introduction to the topic and why forecasting mid-stock demand is important. Next, I'll explain the motivation behind the research, focusing on the challenges of beef demand and supply in Indonesia. We'll then look at the methods we use, specifically comparing double exponential smoothing and double moving average. I'll walk through how we apply these methods to our dataset and optimize these parameters. We'll review the result and see which methods perform best. Afterward, we'll discuss the significance of these findings, and finally, we'll wrap up with the conclusion and suggestion for the future research. Let's start with the introduction. This study focuses on forecasting beef stock demand, which is crucial as Indonesia's economic growth and demand for beef increases. Currently, only 70% of demand is met locally, with 30% filled by imports, making accurate forecasting essential. The goal of this study is to find the best method to manage seasonal fluctuation in beef demand. We'll compare two forecasting techniques, double exponential smoothing (DES) and double moving average (DMA), to determine which the performance is better. In research motivation, beef plays an essential role in Indonesia as a key protein source and a staple in the diet. However, the challenge lies in fluctuating supply levels caused by seasonal demand, climate variance, and market disruption. Additionally, the gap between local beef production and demand creates a reliance on imports, making it difficult to maintain stable supply levels. To address these challenges, accurate forecasting is crucial. It helps bridge the gap between supply and demand, ensuring stable prices, available, and stock levels. This study aims to develop models that predict beef demand more accurately to support better supply chain management. In this method, the dataset used in the study consists of 6 years of monthly data from 2015 to 2020 with a total of 72 records. These records are from 4 districts in Pemalang, representing the mid-stock requirement in tons per month, which are influenced by seasonal patterns. To forecast this data, we use two methods. First, double exponential smoothing or DES, which is an extension of single exponential smoothing, SES. DS is a deal for data with a trend, and it smooths the data into stages for minimizing errors. The second method is double moving average or DMA. DMI captures both trend and seasonality by averaging data points over 2 periods, making it effective for handling seasonal fluctuations. To evaluate the accuracy of this model, we use the mean absolute presenting error or MAPE. This matrix allows us to measure how close the forecasts are the actual data, with the lower MAPE values indicate the more accurate models. This is the proposed method, starting with the figure on the left, which outlines the steps for both double exponential smoothing (DS) and double moving average (DMA). As you can see in the flowchart, we start by partitioning the data into training and testing sets, and then processed into a different forecasting method, DES and DMA. For each method, specific parameters like alpha for DES and the other, and for DMA for optimized. For DES, the figure shows that we first determine the result of the first smoothing and then apply a second smoothing to capture trends. DES uses the alpha parameter to determine how much weight is placed on recent data. It is particularly useful for linear trends. For DMA, the figure illustrates how we determine the first smoothing or SMA, then the second smoothing, and finally calculate the constant and slope values. This method is a better suited for capturing seasonality, as it indicates by the structure of the data we are working with. While these methods, as highlighted in the figure, DS account for both level and trend, while DMA excels at capturing long-term seasonal patterns, making it ideal for our dataset, which has clear seasonal components. The process concludes by evaluating the accuracy of the forecast using mean absolute percentage error or MAPE. As shown in figure, we iterate this process until the MAPE falls below a predefined threshold. These are the results of our forecasting model comparisons, focusing on the MAPE values for both DS versus SAS and DMA versus SMA. The table on the left shows the comparison of MAPE values for SAS and DS across varying alpha parameters. As we can see, SAS outperforms DS in the term of accuracy with a MAPE of 6.52% at an alpha value of 0.9, while DS had a higher MAPE of 8.21% at its optional alpha value of 0.4. On the right, we see the comparison between SMA and DMA based on varying time-ordered parameters. DMA provides the most accurate forecast with a MAPE of 5.993% at the fourth time order, outperforming SMA, which had a MAPE of 6.123% at its optional order of 2. The bar chart at the bottom further illustrates these comparisons. The chart at the left shows the DS consistently outperforms worse than the SAS across all test alpha values. The chart on the right highlights the superior performance of DMA over SMA as the time order increase, especially from the fourth time order onward. In summary, the results clearly show that SAS outperformed DS and DMA significantly outperformed SMA, with DMA emerging as the most reliable method for this dataset based on its ability to handle seasonality. It handled the seasonality more efficiently. Our analysis highlights the importance of choosing the right forecasting method for a given dataset. Simple models like SAS performed better than DS despite DS being more advanced. On the other hand, the double moving average DMI methods outperform SMA due to its ability to smooth out seasonal fluctuation in the data. This makes DMI the better choice for forecasting seasonal mid-stock demand. In conclusion, we found that the double moving average DMA method was the most reliable for forecasting mid-stock demand, achieving the highest accuracy of MAPE 5.993%. DS, while more complex, did not perform as well, possibly due to the seasonal nature of the data. Moving forward, we plan to explore techniques like hyperparameter tuning to enhance the accuracy and robustness of this model. Thank you for your attention and time. I hope this presentation has provided you with valuable insight into forecasting method for seasonal demand. Thank you. Bye.